This lesson is for FST, lesson 8-7 on infinite series. You'll see a capital S for series, and then if you see the infinity symbol, that's your hint that this series goes on forever, meaning it's an infinite addition. Some of the series that we study come from either an infinite sequence or a finite sequence. Infinite sequences are sequences that go on forever. Finite sequences have an ending point. An infinite series could have either an infinite sum or a finite sum. If the sum is infinite, that means it goes on forever, which would mean that it's divergent, which means it has no limit. The sums that are finite are ones that we can identify, and those will converge or have a limit. To determine whether or not it converges or diverges, one of the things you can do is examine partial sums, and that's the first example we're going to do in the video. So we're going to look at some of the sums and we're going to see how they behave. So you can use that method to figure out if it's going to converge or diverge. The convergent ones you'll be able to either tell by looking at the partial sums. There's also going to be a formula that we're going to use, which I'll explain later on in the video. So for our first example, we're going to look at the sequence 4/3, 8/3, 16/3, and so on. There is a formula given here, but sometimes you can look at the sequence and determine what type it is. But that should always be one thing that you do, is figure out if it's arithmetic or geometric. As we look at this, it's pretty clear that you're taking 2 and you're raising it to a power. And so this is probably going to be a geometric situation. Could also figure out if it's arithmetic or geometric by subtracting the second and the first. See if you get the same answer when you subtract the third and the second from each other. You would do the same thing to figure out if it's geometric by dividing the second by the first and the third by the second. And when you do that, you can see that there is a common ratio here of 2. We're just multiplying by 2 each time to get from one term to the next. We've also got a formula here, so that could help us generate any of the terms in the sequence by simply typing in a number for n, depending upon whatever term we're looking for. They want us to write the first 5 terms, that would be of the sequence, and then they want us to look at the first 5 sums as well, so that would be for the series. So we're kind of doing this problem twice. If we're trying to find term 4 and 5, we could either take the previous term and multiply by 2 because we've already determined that the r value is a 2, or you can plug in a 4 in for n into the formula. So I'm going to use the formula to find the 4th term. So I'm going to plug in 4 for n, and then I'm going to use the order of operations to generate the 4th term. 2 to the 4 plus 1 is going to be 2 to the 5th, which I know is 32 over 3. To find the 5th term, I do the same thing. 2 to the 5 plus 1 over 3 is 2 to the 6th, which I know is 64 over 3. So I've got term 4, I've got term 5. Now if I want to look at the sums of those, I'd want to go ahead and start adding 4/3 plus 8/3, and then 4/3 plus 8/3 plus 16/3, and then 4/3 plus 8/3 plus 16/3 plus 32/3, and so on. So I've already got that figured out here. I'm just going to pull that up for you here on the video. So you can see here that the first term is 4/3. When you add the first and the second term together, we get 12/3 or 4. 4/3 plus 8/3 plus 16/3, and we get all of our answers there. So these are all the sums now in the series. So I do want to go ahead and get answers for these because that's going to help me answer the other piece to this question. Does it appear to converge? Keep in mind that that's a yes or no question, so you're either going to say yes or no. So I'm going to go ahead and get a decimal answer for all of these sums to help me determine the partial sums, or at least the first 5, to see if I can determine if it's converging or not. So I'm just calculating 28 divided by 3, 60 divided by 3, 124 divided by 3. And I'm seeing here that we started it with 1 1/3, and then we moved to 4, and then 9, and then 20, and then 41. And so the difference between these sums keeps increasing, and it's just going to continue to increase as I add more and more terms. So I can tell by just looking here that this is going to be a divergent situation because it's just going to have an infinite sum it just grows and grows over time. So does it appear to converge? I'm going to say no there. Most of the time the question will say, is it divergent, or does it have a limit? And so then you'd either say no, divergent, or you'd give what the limit value is. But this one is a yes or no question, so we're just going to say no, it does not appear to converge. And we did that just by looking at partial sums. Most mathematicians don't like this method because it doesn't really seem like it's very mathematical. All you're doing is calculating, and then you're just kind of using your gut instinct. These numbers seem to grow, so we're just going to say no. So there's got to be a better way. And there is. The book explains on page 545 that when you're working with a convergent infinite geometric series, there's a way to tell from the formula. So there are some really good infinite geometric series covered in the lesson, which I'm not covering in this video. You might want to look back at example 1 in the book and then the activities, because there's some that do and some that don't converge. So how can you determine whether an infinite geometric series converges without having to add those terms together? The key is the common ratio of r. If r is between -1 and 1, then it's going to be a decimal or a fraction, and therefore each new term would get closer and closer to 0. However, if r is greater than 1 or smaller than -1, then each successive term would get farther away from 0. This suggests that convergence or divergence of a geometric series is dependent on the value of the common ratio r. So before we look at what the formula actually is, let's go back to our title. What we're really focusing on today is infinite geometric series. We have a formula for how to determine if an infinite geometric series converges or not. We'll talk later about the arithmetic ones. So the formula for an infinite geometric series is all determined on the value of r. If r is between -1 and 1, then the series will converge, and its limit will be this very simple formula, g sub 1, or the first term, divided by 1 minus r. If you calculate that, that'll be the number that the series converges to. That'll be its limit. If the r value is greater than 1, or not a fraction or not a decimal, then the series will diverge. The arithmetic ones, which I'll give you a graphic for shortly, or at the end of the video here, the arithmetic ones will diverge because you're just going to be adding over and over and over again. So I've got 4 examples that I want to look at here in the video to help students solidify their learning. The first example is a sequence. So this first example is actually from what we learned back in 8.3 about limits. If it has a limit, it will have, in sequence form, it'll have a horizontal asymptote. So what you'd want to do is come up with an equation for this sequence, determine if it has a horizontal asymptote. If it does, then that would be your limit. But you would not use the information in this lesson to make that decision. This may or may not be infinite, but we don't care because it's a sequence. Sequences, to determine if they have limits, we use horizontal asymptotes. So in this lesson we would say here this is not a series, and we could just quit. But since we're using this as practice, if we're given a sequence and asked if it has a limit, we would simply determine if it has an asymptote or not. So if you look at this sequence, the first term is 5/3. And then if you do some quick division here, you can clearly see that if you do 5/9 divided by 5/3, you can see then that the r value is a 1/3. And so if we graph that on a graphing calculator using x as our exponent and x as our variable, you'll get an exponential decay curve with an asymptote on the x-axis. So the limit of this sequence as n goes to infinity, so I'm just going to call this question A, is going to be 0. But not because of the information in this lesson, but because we graphed it because it's a sequence. The next problem, problem B, is the same numbers but now in series form. This does go on forever, so it's an infinite geometric series. I know it's infinite because it says dot dot dot. I know it's geometric because I already examined its sequence in the previous question. So to determine if this infinite geometric series converges, I look at the value of r. r is 1/3. That is between -1 and 1, so it will indeed converge. What it converges to is this little formula. The first term divided by 1 minus the r. If I calculate that, I get about 2.5. So that is the limit of b, question B, as n goes to infinity. So then that's my answer. Similarly, for question C, we're going to look at the fact that it's a series. I want to determine if it's arithmetic or geometric. Am I adding to get from one term to the next, or am I dividing to get, or multiplying to get from one term to the next? So I'd want to see if the difference here is the same as the difference here, or if I'm multiplying to get from one term to the next. And if you don't know, you'd want to do some subtracting. 160 minus 640, 40 minus 160, those aren't equal. So then we do division. 160 divided by 640 and 40 divided by 160. When you do that, you end up getting an r value of 1/4. So it is indeed a geometric situation. It is a series because we're adding. And the r value is less than 1. So that means we're going to use the same formula we did on the previous. First term divided by 1 minus the r tells us what the limit converges to. When you calculate this, you get about 853 1/3. So that is the limit of question C as n goes to infinity. So that's a very handy little formula, isn't it? If you're working with a geometric infinite series, figure out the value of r, and that will help you determine whether or not it converges. Our last one here is D. Again, it is a series and it does go on forever, but we want to determine if it's arithmetic or geometric. And you'll see that there is nothing you can multiply by to get from one term to the next. We are adding here. So this one is arithmetic, so it's going to diverge. Arithmetic ones keep adding over and over again. They're just going to grow and grow over time, so they do not converge to a single number. They just get larger and larger. To illustrate that in summary, when you have an infinite arithmetic series, it will diverge. If you have an infinite geometric series, you want to look at the value of r. If r is greater than 1 or less than -1, it will be divergent. Only the infinite geometric series with an r value in between -1 and 1 will have a limit, and the limit is calculated as g sub 1 over 1 minus r.